Hello, my name is Francisco, and today I'll talk about lines in 3D. But what is special about lines in 3 dimensions, and what's the difference between a line in 2D and 3D? Well, the main difference between line in 3D and 2D is that lines in 3D don't have a slope. They have an initial position and a time-dependent vector that define their value, just basically v, velocity. So they have the vector position r is going to be equal to their initial position r naught plus their velocity times time, vt, where v is equal to a comma b comma c. We can break that down into components and have the x, y, and z equations. X is equal to x naught plus at, y is equal to y naught plus bt, and z equals z naught plus ct. This is the parametric equation of a line. We can also solve for t and set them equal to each other. And then we end with that. X minus x naught over a is equal to y minus y naught over b, and z minus z naught over c. This is the symmetric equation of a line. Just a quick note, a cannot equal 0, b cannot equal 0, and c cannot equal 0. But what can we do with this? Why does it matter? Well, we can see when two lines intersect. And there's 5 cases. When the two lines are parallel to each other, there's going to be a distance, d, between both of them. And since they're parallel, they'll never intersect. So that distance will be there forever. There's also the case where the two lines start at different points, but they're essentially the same line. They have the same v vector. And then there's going to be a distance d also between them forever, because the second one will never be able to catch up to the first one. And there's the case when they have the same initial point and the same velocity, so they'll be together forever in case 3. Case 4 is when the two lines do intersect at some point, at some time t, right there. And then there's the case 5 when two lines are slant, meaning they have the same position in two components, let's say x and y, but not z. So what happens is that they'll go right on top of each other like this, but they'll not intersect because they have different heights. Well, but where can we use that? One example is two airplanes colliding. Let's say we have airplane 1, vector 1 is given by the initial position -2, 5, 2, and the velocity vector 2, -1, 3. And the second airplane has the initial position 0, 2 over 3, and 3, and the velocity vector 1, 2, 3. Well, with this, we can find their positions with these equations. We can just break it down into their components, and then we can see when they're equal by setting them equal to each other. So if we let x1 equals x2 and z1 equals z2, we can actually solve for t prime. And then we just plug t prime back in there into z1 plus z1 equals z2. And then we have 2 plus 3t is equal to 3 plus 3 -2 plus 2t. Here is really easy. You can solve for t, and you end with t equals 5 over 3. Now you plug t back in there, and then you have t prime is equal to 4 over 3. Now we found their time. Now we need to see if their position will be the same at that time. It's really easy to check for x1 and x2. Since we set them equal to each other, we know for a fact that they'll be equal. Here we can just plug in t prime back into x2, and we see that x is going to be 4 over 3. Plugging t into z1, you end with z is equal to 7. That's true for both of the vectors, both airplanes. Now, what we need to check is if their y's are equal to each other or not, because that would define if they're slant or not. Solving for y1, just plugging t in there, 5 over 3, you end with 10 over 3. If you solve for y2 and plugging t prime into y over 2, you also end with 10 over 3, which means they do intersect. So the point in which they intersect is 4 over 3, 10 over 3, and 7. And here I just went ahead and I graphed it. So this is R1 and R2 right there. R1's here, R2's right here. And then T, sorry about that, T is equal to 5/3. And T prime is equal to 4/3. So from this, we can tell that the two airplanes do crash and everybody dies. So yeah, very sad. Okay, thank you very much. Bye.